Hello everyone. Thank you for joining this webinar organized by the XFlow team of Dassault Systems Simulia. My name is Zaki Abiza. I'm from the XFlow business development team. In this webinar, my colleague Rudy Briono, our lead XFlow application engineer, will show you the XFlow results we presented last June in Denver at the third AIAA CFD High Lift Prediction Workshop 2017. Before I hand over to Rudy, I want to inform you that you can send us your questions. So through the questions dialog box that you have at the right of your webinar interface, just here, as shown in this slide. So feel free to send us your questions during the webinar. I will try to answer some of them during the webinar, and some of them will be answered at the end of the presentation and the Q&A session at the end. Thank you again for joining us. I will let you now with my colleague Rudy. So go ahead, Rudy.
Thank you, Zaki. Thank you very much. So hello everyone, good afternoon or good morning, wherever you are. So let me introduce you today to the results we obtained for this high lift prediction workshop. So this is a pretty good and well-known workshop in the aeronautical industry. So for the outline today, we'll first introduce actually what the high lift prediction workshops are, because there are a few sessions. This is the third edition we've been participating to, and speak very briefly about the numerical methodology of XFlow for those that maybe don't know XFlow yet. Then we'll speak about the configurations of these high lift prediction workshop 3. What were the different configuration of aircraft we have to simulate, and the conditions of flow to model. And then we'll see the aerodynamic results of those analysis with XFlow, and then finally a short question and answer sessions in case you have any questions. So as Zaki mentioned, you can feel free to write down your questions in the question box on the panel on the right in the meantime. So let's get started. First, a short and brief introduction to the high lift prediction workshops that have been conducted in the past. These workshops basically started in June 2010, where the first edition took place. They are organized by the AIAA, so this is the American Institute of Aeronautics that organized these in cooperation with the NASA, but also a lot of different institutions like Boeing, DLR, JAXA, and so on. So all these aeronautical institutions gathered, and they built some of them built like some models, and they tested it in wind tunnels. Then they provided to, well, participants that were keen to actually simulate this kind of high lift prediction analysis data, on which they could compare their CFD simulations with the wind tunnel measurements. So the very first edition was made on these NASA trap wings. That's because it's a trapezoidal wing shape. As you can see, it was, well, rather simple to start with, in the sense that we don't have any fuselage here. It's just mounted on a base, but you basically mostly have a short span wing, and still you got the slap and the flap elements, so it's a three mm blades, okay, wing. So in this case we had to predict also the polar curve for these aircraft. That means at different angles of attack, trying to estimate what the lift and the drag forces are on this geometry. Then we also, so you can see, for example, some animations of the predictions we've done in the past for these workshops, the different workshops. And then in June 2013, another edition actually showed up, and then this time it was made with the DLR F11 high lift configuration. That's a model that was built by the DLR, so which is the special aerospatial agency from Germany. And they also measured like a lot of data, especially they had a lot of additional data on the flow fields like oil visualization techniques and this kind of stuff that provided a much still better insight in the flow field. Okay, and so the third edition came now. That's the one we'll see today, with another model from JAXA, which is a Japanese aerospace institution. So just a few words on the methodology that we use with XFlow. It's based on the Lattice-Boltzmann method, in case you don't know XFlow. That's just a brief summary. We don't use a classical Navier-Stokes approach to resolve fluid problems. We use the Lattice-Boltzmann methods, which is also called LBM. It's a method that works at mesoscopic scale. That means unlike, for example, the Navier-Stokes equations, on which we normally apply typically some finite volume and finite differences or finite elements methods to resolve those equations. Well, you don't work with velocity and pressure at macroscopic scale, but instead you work at mesoscopic scale. So you can just like watch a small portion of fluid, a small particle of fluid, and modelize the behavior of that fluid with distribution functions that will basically, each of the functions model like the macroscopic behavior of the flow fields. Okay, and this is based on the Boltzmann transport equation, which is basically composed of two terms, a streaming term on the left and a collision term. So we just stream and collide on a lattice, which is this cubic structure you can see here. So every PDF that you have on different directions, the particle distribution functions are streamed, okay, to the neighbors and also collided. Okay, that's how the scheme is working. Okay, so we won't enter in detail today. In case you want some more details about the method, of course, feel free to contact with us. So we use a specific central moment collision operator also that improves accuracy and lowers the numerical dissipation. And let's say in classical CFD terms, Lattice-Boltzmann is pretty much an explicit scheme. Okay, it's inherently transient because it's a Lagrangian method, and it's second order in time and space, mildly compressible. Also, we discretize the space not with a typical mesh. Normally you have to mesh your fluid domain to make this CFD analysis, right? Well, in this case we use what we call a lattice. Lattice is like a mesh, but it's actually like a network of points. So imagine you've got discrete points in space, and only on those points you've got information in this case. And these points, they have different velocity directions on which the particle distribution functions can be streamed and then collided. So the lattice structure is an octree structure. In fact, you don't have to use a uniform lattice spacing across your entire domain. You can actually also use different resolutions at different locations. For example, if I want to refine near my cylinder, I could have actually some finer, smaller cubes in some regions and others. Basically, you can just take one of the voxels that represents like a small fraction of fluid around the lattice node, and you can split that voxel into 8 voxels, and then again split it into 8 voxels again. Okay, so let's say the time steps, not only the spatial scales, but also the time scales are divided the same way, following the same ratio. Every time you divide by 2 the space, you divide by 2 the time, and so on. So you have a constant dx over dt, let's say, ratio across your entire domain, so a constant CFL condition. For instance. And for the turbulence, we use actually an LES turbulence model, okay, which is a wall adapting local eddy. Okay, LES is known to be a high fidelity model to describe turbulence because we resolve the turbulence spectra up to certain scales, and then for the smallest eddies, we don't resolve them anymore if we don't have a lattice size that is fine enough to discretize an eddy, for example. We will just apply an LES turbulence model in this case. So the LES turbulence model has a strong advantage with Lattice-Boltzmann to be a very low cost compared to traditional methods. Okay, and we also use a generalized law of the wall that is used for the wall treatments, especially to predict what the boundary layer is, because usually since you've got a lattice, it's a Cartesian structure, so it would be extremely tedious to actually try to refine within the boundary layer with such a structure, a Cartesian structure, especially around a curvaceous area. And so we use instead a law of the wall, okay, that describes the boundary layer behavior and takes into account for adverse and favorable gradients as well to predict separation of the flow and so on. So it's, as you will see in these high equation workshop results, a good combination between LES and the near wall treatment. Okay, for the near wall treatment, as you can see, the way to treat the walls is very easy in XFlow and with the lattice-Boltzmann method in general, because you don't have to mesh. That's a very strong advantage because it saves you a lot of time. All you need to do is import your geometry, like this solid you can see here, and set a given lattice size. And the lattice will just like create all around the solid, and as you can see, every time a lattice node will try to connect to the neighbor, it will eventually intersect with the walls of the geometry and then can create a dot, like you can see the yellow dots here, representing one surface point of information on the surface, okay? So you can discretize with a relatively high discretization order with just a few lattice nodes, because in our case especially we use a D3Q27 lattice scheme, which means every lattice node can see up to 27 directions of velocity, which is a high discretization order. Okay, that was a very short introduction for the lattice-Boltzmann. It's a long topic, so I won't explain everything today. But in case you're interested in knowing more about this methodology, please feel free to contact us, okay? We'd be really thrilled to actually explain you the methods and give you some presentation about that. So let's keep going, and now we introduced the previous high diffraction workshop that we've participated in the past and that also took place in the past. But this year it was a high diffraction workshop edition number 3. And there were a lot of cases, okay? We focused on the main ones, which were basically the mandatory cases, okay? But there were also more cases. You can feel free to Google high diffraction workshop. You'll get on the web page. You've got a lot of description information here. You can see all the test cases. But we focused on the 3 mandatory test cases, which were case 1A, 2A, and 2C. Okay, so there are like difference between case 1 and case 2 is mostly the aircraft and the type of aircraft model, and then between case 2A and 2C you'll see it's a small variation in geometry. Okay, so for example you can see case 1A is the aircraft you can see here. Okay, they look the same size because we've put them with the same size on this picture, but in reality this aircraft here it's a well, larger size model, okay, it's a 30 meter semi-span wing, okay, and mean aerodynamic chord is about 7 meters. It's a real scale model, okay, that's 1-1 model here for the case 1A, and for case 2A and 2C, these are wind tunnel models, okay, so that's scale models, and you can see that the wing semi-span is actually 2.3 meter in these 2 examples here, and the mean aerodynamic chord is about 0.5 meter. Okay, so basically these 2 models from case 2A and 2C had experimental data available. They are models that are the JAXA standard model. Okay, one is without the nacelle and the other is like with the nacelle. Okay, you see that case 2A is without nacelle, whereas case 2C has a nacelle included. Apart from that, they're exactly the same case. And these 2 models have been developed by JAXA, and they've been tested in their wind tunnel facilities, and they provided an excellent set of data, very complete, that is also available on the high diffraction workshop website, so feel free to check on that. For the case 1A, it's a bit different. It's a real size model. It's not tested in wind tunnel, at least not yet, okay, not at the moment. So basically the objective for case 1A was just to proceed in a resolution study. Okay, we got let's say a case, we don't have any reference data, but we want to see where our aerodynamic forces converge with the grid solution, okay, with the grid resolution. Whereas the objective for case 2A and 2C was the polar prediction. In this case, we simulated a very long list of angles. Well, in this case 5, and it's not so long, but it's quite a few angles so that we can capture the linear part of the polar and also the stall entry and the post-stall mechanism. Okay, so from 4 degrees to 23 degrees, actually from 0 degrees, sorry, to, that's what was, I think it's a typo mistake, sorry, it's a 1047 here, but that's from 4 degrees to 23 degrees approximately, okay? So in the case 1A, we only did 2 angles that were the 2 requested. These 2 angles are in the linear part of the polar, so not in the stall region yet. Those cases are well, about a few million for the Reynolds, 3 and 2, and well, low Mach numbers, moderated Mach numbers, 0.2 approximately, because we are in a landing and taking off configuration. So we did the 3 cases, and we'll show the results for each of the cases afterwards. But here is how we did the setup in XFlow. Okay, so we got this virtual wind tunnel. It's a preset of boundary conditions where you got inlet velocities, pressure outlets, and we've put a ground wall which is a free slip ground wall. It's actually to made let's say the symmetry condition in the wind tunnel anyways. The aircraft is actually lying on the floor as well, so we just put that ground so that the aircraft is lying on the ground as in the wind tunnel. In the lateral boundaries we had some periodic boundary conditions, which is good enough in this case since we have well, sufficient spacing between the lateral boundaries as well. So what we do is we actually increment the incidence of the wind velocity profile at the inlet components. Okay, so we just kept the same model with the same position for the different angles of attack, and we just increased velocity of the inlet velocity profile. So these are the lattice we used. Okay, so it's an introduction. It's so again, it's not exactly a mesh, but imagine that's basically the mesh we use for our CFD analysis. And you know, the committee for these workshops usually provide a mesh that all participants need to use, for all Navier-Stokes code need to use, or are, well, invited to use at least, because of that we can compare like all participants in a fair way with the same meshes and just see the impact of the solvers independently of the mesh. We can't do that, okay, because we're lattice Postman method code, and consequently we had to generate our own lattice structure because we don't work on meshes, okay? So we had to generate different meshes, well, grids or lattice, call it as you want. And the lattice generation is automated based on the geometry and the resolution you put. So you have to specify just a few inputs, like what is a far field resolution, the spacing between 2 lattice nodes at the far field, and also the spacing between 2 lattice nodes near the walls. Okay, and it took on average maybe 30 minutes on 6 cores to generate this lattice, so it's pretty quick for the biggest lattice, of course, so about 100 million elements as the biggest lattice, about half an hour. For the others it's a bit faster, but it's a very quick process usually, and all automated, so it's a really gain of time here. So you can see that we made 3 meshes for the case 1A and 1 only mesh for each of the case 2A and 2C, okay? Because we have to make the grid dependency study for case 1A, whereas the case 2A and 2C is just computing the entire polar curve, okay, the forces at different angle of attack. So for the, let's say the case 1A, we've got a far field resolution of 5 meters approximately. That's a real scale model here, so you'll see that there are disparities between the units in case 1 and case 2, because the case 2 is a small model of 2 meters, whereas this one is about 30 meters span. So it's a different type of scale. So here we have 5 meters at the far field, and we start with 4 centimeters near the wall of the entire aircraft, fuselage, flaps, slats, wing, everything. Okay, and then we do 2 centimeters and then 1 centimeter. That's a consistent way in lattice Boltzmann to refine and do a grid convergence study, because in this case you can, every time you split by 2 the spatial dimension, okay, so resolution of the lattice, then you split a cube into 8 cubes and then again into 8 cubes and so on, and you don't display somehow the lattice sites, you just like split your voxels into smaller voxels, okay, so it's a consistent approach. So you can see, of course, since it's a Cartesian structure, it increases, well, very very fast when you refine, of course. So you go from 17 to 50 million to 107 million elements in the first case for the fine mesh, and then for the second case we use a medium-sized mesh of 2 millimeter near the walls and 5 centimeter at the far field, and that gave us approximately about 30-40 million elements. Okay. So you get an insight on the type of mesh we used for these analysis. So you see on the left it's case 1A. Okay, that's a fine mesh here. You see, so that's a zoom here on the slat. Okay, you can see it's pretty nice, pretty nicely resolved. And on the right side, it's a medium-sized mesh. You see, it's a little bit coarser, but still we've got enough elements to discretize that gap here, as you can see, and to discretize the profiles. You can see it's like a step-like pattern, but remember the previous slide I've shown you, every square near the wall can see up to 27 points on the wall. So in reality, it's not this step-like pattern is not actually happening inside the solver, okay? It's just the points in the space where you know velocity, pressures, and so on. But the discretization of the profile of this profile of wing is actually at a much higher order in the underlying iterations of the solver, okay? So don't be tricked by this aspect. It looks like it's a bit rough, but it isn't. Okay, so that's the configurations, the grids. What about the results? So now we will present what we got from these analysis studies. So the first case, as I said, was a convergence study. Okay, so we don't have any data, any experimental data to compare with. So it's a bit hard to tell you how far we are from what the solution should be. But it's important to see first the evolution with the resolution, and secondly, also, since it's been a workshop where a lot of people participated, well, the difference between participants. So 2 things. These 2 graphs here describe the convergence in lift on the top and in drag on the bottom. You see, well, it's not very nice because both curves have the same color, but you've got one curve for 8 degrees and one curve for 16 degrees angle of attack, the same for the graph below. Well, the highest lift and drag value is 16 and the lowest one is 8 degrees, of course, okay? So you see that basically it's a graph that plots the lift and the drag in function of n power minus 2/3. Okay, it's a way of checking convergence. And so when you go on the left, for example, you can see that it's where when you refine your resolution, and when you tend to 0, it's when you tend to, let's say, refining to an infinitely fine solution. Okay, when the distance between 2 lattice nodes would be tending to be 0. Okay, so basically you've got something that you can see does sort of almost linear trend, and you see that you should converge to something. Okay, and apparently what's interesting to see is that we highlighted in red from the summary available on the high lift prediction workshop. We highlighted sort of graphically the difference and the scattering between the results of the participants. Okay, so that's basically the reddish area is basically where all participants converged finally with their solution as well. And so what you can see, it's interesting 2 things. I would say first, there is much less scattering in the drag coefficient than in the lifts. And secondly, also we can see that we converge towards, well, what most participants predicted. So that's apparently at first sight a good sign of convergence, because that's a low angle of attack. So we know for these linear angles and the linear part of the polar, usually the predictions of most participants should be good. Okay, so we are within the range of the other participants. It's interesting to see that there is more dependency on the resolution of the lift than the drag as well. So we wanted to see exactly what the resolution is affecting. Okay, where are the regions sensitive to the refinements? This is where we actually started to create some cuts of pressure distributions. So we just take different slices. You see all the red lines represent a plane where we evaluate the pressure distribution on, well, the slats, the flap, but also the wing. Okay, and what you can see is that we have the plane 1, which is here on the top left, and the plane 8, which is on the bottom right. So 1, 2, 3, 4, 5, 6, 7, 8. And that's basically plane 1 is basically near the fuselage, and the more you increase, the more you go to the wingtip. Okay, so this is near the fuselage here, and this is near the wingtip here. Okay, so what we can see is I would say, between green, which is coarse resolution, blue is medium resolution, and red is fine, there is especially a high discrepancies in these area you can see here, especially at the outboard flap. Okay, so outboard flap is basically this flap here. This is this part. So you got the kink here, and then you got the inboard flap. Okay, we can see a higher sensitivity of the grid resolution. You see that between the coarse and the fine mesh, there is a huge difference in trend here, especially between the coarse and medium, okay, or the coarse and fine. The medium and fine have some differences, but they are relatively similar profiles. But there is a really change of topology of the flow here, okay, and that's because we assume is that the gap in between the flap and the wing is important to be resolved. And as you may know, the gap between the wing and the flap is reducing as you go to the outer, let's say at higher span position. Okay, so basically the gap is very tiny in these areas here, whereas it's larger in these areas here. It's important to resolve very well this gap in between the blade elements to resolve the flow mechanism correctly. Okay, otherwise, if you don't refine sufficiently those gaps in this region here, you may just consider, as you can see on the green curve, it's almost a continuous blade element. It's like if it was a one element blade, a one element wing. Okay. So basically we need these peaks here to capture the correct flow mechanism. So that was for 8 degrees, but for 16 degrees it's pretty much the same thing. Okay, we see the same discrepancies happening, especially again at the outboard wing. Okay, and we see that there is separation for the coarse resolution. The region here seems separated, whereas the other maybe are not so separated and not separated at all even here. So you can see that there is a real difference between, especially again, the green and the others. Okay. So when you look at the flow field, you really appreciate that better, I think. And now you can see that the coarse here, the medium here, and the fine here, this is a volumetric rendering of vorticity. So you can see the vortices in 3 dimensions on the blades, on the wing, not on the blade, on the wing. And you can see all of them present like this strong vortice that goes from the slat beginning here. But the main difference is in this area here. We can observe a separation area that occurs in this outboard region again, outboard flap region, and doesn't occur, for example, for the fine and the medium meshes. Okay, all of them, or at least the fine and the medium ones, have like this small separation occurring at the kink here, which makes sense in this region, but this separation doesn't occur here and there. Okay, so we see really a jump again between coarse and medium and fine. When you take a cutting plane at plane 6, which was approximately where the separation occurred on the previous slide. For the coarse case, you can see it clearly. Okay, you can see that maybe you see the voxelization, it's like squared on the lattice. It's because of that allows to appreciate the lattice size we use for the simulation, which is pretty coarse. Okay, and we can guess that that resolution, that size of cubes here are probably too coarse in this region, in this gap here as well, which means you've got a continuous blade element almost. It doesn't discretize the gap here and the flow cannot flow out from there. Okay, that makes a huge difference in the mechanism of the flow then, and will induce a large separation on the flap. Okay, that doesn't occur as soon as you refine in these regions, probably because you can allow the flow to pass better and evacuate through the gap in between those two elements. Okay, so you've got the effectiveness of the high lift device better modeled in this case. So what we've done as a final test for this convergence study is that what about if we just refine in the gaps, or at least on the flap and slats, so that we can see the impact on the solution. Okay, and that's what we see, that if you take, for example, a mesh where you got, let's say, the medium lattice size for the main blade, but you take the fine lattice size just on the slat and the flap, then you actually realize that if the blue curve here is the medium mesh and the red is fine mesh, you realize that the this mix of fine resolution just in the slat and flap, and consequently in the gaps as well, makes a huge difference. Okay, it makes a huge gap, and makes the this kind of refinement, local refinement, to catch up with the fine resolution, but at a much lower cost, of course. So you see, it really highlights that it's extremely important to well resolve these regions properly, especially like the leading edge of the slat here, also the gap here as well, which is important to guide the flow towards the main wing. And will precondition a lot the flow on the main wing then, but also like this gap here as well. And you can see that the fine and the mix between medium, the wing medium and the slat flat fine is approximately the same flow patterns. So it's very close. So we just basically highlighted the importance of not refining necessarily everywhere, but especially in some given regions, critical regions that are those elements. Okay, so that was for the first case. Now we'll switch to the second case, okay, directly. That's the JAXA model, okay? And as we said, in this case here, we do have comparison data, experimental measurements, okay? Which are the polar curves you can see here. So on the left side, you got the lift polar, the drag polar, and the polar curve, which is drag, lift against drag coefficient. Okay, so here this is the lift coefficient against the angle of attack in degrees, the drag coefficient against the angle of attack in degrees, and the lift coefficient against drag coefficient. Okay, so what you can see is that there is clearly a very linear region from 0 to 20, or even maybe 15 degrees, and then you start to have a decline of the slope of the curve, and finally you've got a maximum lift value at a certain angle, which is around 20 degrees, to be exact, 20.09 degrees from the experimental data. And well, the game is basically, okay, trying to capture these parts here of the polar, the entry and stall, because that's when your aircraft is actually doesn't have any lift force anymore. Okay, so that's the dangerous situation. So you can see that in the case of XFlow, the linear part is well predicted in terms of curve, in terms of absolute value, and also we detect the maximum lift value. That means the maximum lift the aircraft force the aircraft can actually carry pretty well, and then also separation at the correct angle. Maybe the stall entry is not as strong than in the experimental data, but we see that at this angle here, let's say the flow is already separated somehow. We already reached the maximum lift point. So you see that we've got a very low difference in stall angle prediction and in the stall value predicted as well. There is slight drag over prediction, But if you check on the summary of the high lift prediction workshop on their webpage, there's a presentation showing all participants' data. And it's a trend that everyone has seen that the drag values were over-predicted by all participants. So basically the committee is suspecting that it might be some wind tunnel effect somehow, okay? So in the end, we've got a polar curve which is pretty well in line, slightly shifted because of this higher drag value, but it's a nicely parallel curve in this case, so it's well predicted as well. So this is a case 2A. That means here we got a case without the nacelle. Okay, so in this case we also can look at a better insight in the flow field, like these visualization techniques they have in wind tunnel that allows to, for example, see oil path lines. So you can see pretty much the areas of separation and the different flow patterns you've got on your wing. So it's very interesting. It gives a extremely good insight in the flow and does, permits like to not only see if you're predicting the correct drag and lift, but also see if you can correct the correct flow mechanism, which is most important, I think. Okay, so when you actually see these and XFlow on the right side and the wind tunnel images on the left side, what you can see here is the near wall velocity projected on the wall from the first lattice elements projected on the wall, and with some thing we call line integral convolution, which is something that gives you the lines basically to give you the direction of the flow. And you can really appreciate the same types of patterns that are these strips that we can see. That's a V-shaped strips you can see here, there, and there. All these, they are due to the slat track fairings, which are the small elements that are joining the wing and the slats. And of course, they are below on the pressure side, but still they're affecting the flow through the gap. That's where we're saying the gap is important in the high lift devices. Well, they affect also the suction side, and also you can see the flow impact on the suction side from those devices that join these elements. Okay, so we can see they're aligned pretty well with what we can see in the wind tunnel at different wingspan position. So this is for 10 degrees, so that's a very moderated flow angle. We also see like the flap has some separation in the same area around here. Here it's separated as well as the same as in XFlow here, so it's pretty encouraging. Then when you increase to 18 degrees, what we observe mostly is the main flow difference. You see if I just switch from one image to the other, we see most of the flow remains similar, I think, but mostly it separates from the wingtip at this angle. It starts at least to have that bubble of recirculation increasing, okay? That's pretty much something we also clearly see in XFlow, maybe not as strongly, but very similarly. There is like an increase in amplitude in the separation in the region here that increases towards the wingtip a bit more. Okay. And more interestingly, when you increase to 21 degrees, okay, you see that the separation bubbles starts forming from now not only the wingtip, which is again much larger still than the previous angle, but also from the fuselage, okay? So you've got a large separation that occurs in the intersection between fuselage and wing, basically, which is especially happening in this back region here. And this is also something we observed in XFlow. As you can see, this region increases, and at then the next angle, this region increases much more. So we've got a large separation that starts growing here and there, okay, in that direction. So we compare here with 23.5 degrees against 21 for one single reason, is that since we slightly predicted slightly late the stall entry, we have to compare with the equivalent level of lift, okay, of the stall entry for both curves. In order to compare the same flow patterns, you have to be at the same level of lift, okay? So maybe this region is slightly over-predicted compared maybe to what is in the wind tunnel, but these two here are pretty nicely captured. We could also think that maybe the resolution on the outboard gap, on the outboard flap gap, is maybe also here one of the causes that, let's say, highlights a higher separation than what it should be. So maybe refining in these regions could improve the flow also in these regions, but overall it's pretty good. And then the case 2C is very nice as well. It's now the same case but with a nacelle that they put on. And you can see that the polar is actually even better matched, I think. Still a slight over-prediction in drag that has been also predicted by most participants, but overall the polar curve is excellent. Okay, so you got same, well, we don't exactly know where the maximum angle is because we only have 3 points in this region, but it's we see the trend is very similar in the maximum value of lift and also again on the angle of prediction. And here again we can compare the flow patterns, and you can see the impact of the nacelle is very nicely described. You've got this recirculation region that occurs at the intersection of the slat wing and nacelle, generates like a sort of vortice that goes in a sort of diagonal direction, really like in the wind tunnel data. And as you increase the angle of attack, again, you see that the separation here grows. Here you don't see so much of separation yet because you've got a large impact of the nacelle that redistributes the flow towards the fuselage, let's say pushing these separation and then delaying the separation. But as you increase to, again, a higher angle of attack, you can see that still the separation occurs. We've got, well, the nacelle separation occurring, going against the near fuselage separation area and also the wingtip separation here, which occurs again pretty nicely as in XFlow. So it seems the postal mechanism is correct. It's not that we see that the main separation area occurs at mid-span or something. It really occurs in the critical regions that are described in the flow field by the experimental facilities. Okay, so that's something that helps us understand if we're predicting the stall for the correct reason, for the fundamental correct reason. Okay, it seems it's okay. So again, a slightly over-predicted maybe region for the close to the outboard flap, but overall it's pretty good. And this is an animation of how you can see the flow, instantaneous flow field. That's a vorticity volumetric rendering of vorticity at 2000 hertz at 23 degrees. So it's like in the stall region. You can see the large separation, of course, coming from the intersection between the wing and the fuselage, which causes probably the separation area to grow from this region here. We see really nicely the impact of the nacelle on the wing flow, and especially near the mix with the fuselage. We see this circulation here a bit overestimated as well again, and we see very nicely the wingtip recirculation here, which is very nice. Okay, so it's the beauty of the of the turbulence and the aerodynamics. And finally, it's just so that you can compare and see, well, are these results good? The answer is yes. That's a very complex aerodynamic problem. It's not easy. This workshop has been participated. I think we had like 35 or 40 participants this year. A lot of people have a lot of interest for this kind of simulations. They are not easy because the geometries are complex. It's hard to mesh for most participants. It's a complex flow structure with the flow around the flap, the gaps between the blades, and so on. And in the end, the stall entry is complex flow structure here because that's where a lot of unsteadiness occurs. And we see that clearly, basically, so just to comment, these red curves are all the participants, the results that have been put on the same graph. That's also available from the summary, available online on the website of the high lift. And you can see one thing is interesting is that, well, first the linear part, of course, have really a very small scattering between participants. Most people manage to just capture very nicely this region of the linear part here. But we see that almost no participant is able to go to the postal region, or they describe an install entry very early. You can see here or there. Most participants, let's say, overpredict the separation maybe at 16 or 20 degrees eventually, or some don't predict the separation at all. But only a few participants are able to manage to get such a postal description of the flow. It's even nicer, I think, on the nacelle case, where you can see the participants really, I think, overpredict against the separation at 21 degrees. It's extremely hard for a steady state code to converge in these conditions here, because the unsteadiness of the flow becomes strong. You've got a lot of separation, massive separation, which is hard to predict if you don't use a high fidelity turbulence model, and it's not an easy CFD simulation. It's also a big simulation. You see that the meshes were 50 million or 100 millions, or some participants go to 200 million elements. They run on huge clusters and so on. Okay, so it's a pretty expensive simulation for most people as well. Okay, and this is a summary. We're, I think, on time. We got basically, for case 1A, we've seen that the convergence is really highly sensitive to the refinement in the slat and flap gaps, okay, especially on the outboard flap. We see that if we refine correctly in those regions, we accelerate the convergence. And we've seen that the forces predicted by XFlow were basically within the range of results found by other participants, so this is a good sign. For case 2A and 2C, we've got basically polar curves that are in good correlation with wind tunnel measurements. The stall is captured with good accuracy. We've seen that the CL max is pretty well predicted. Stall angle is slightly higher, but very close. And more importantly, we also check with oil path images that the flow patterns are correct and the flow topology is correct even on the post-stall mechanism, okay? So we really predict the stall entry for, fundamentally, it seems as a good reason, which is important. And finally, I didn't comment, but for a lot of participants, just including something like a nacelle, in your analysis can be just a nightmare, okay? It can be like weeks and weeks and weeks of work just to introduce such a geometrical element, include that, mesh the fluid domain, because the geometry becomes much more complex. The gaps in between the flap and slat are complex, but also introducing the nacelle is complex, it's time consuming. While for XFlow, for us doing case 2A and 2C, when we had case 2A, basically it was a matter of 1 hour to put in place like case 2C and run them again, because it's just like importing an additional geometry that is the nacelle. Well, you had different geometries for the wings as well to adapt the nacelle in the wing, but basically it's just importing new geometries and just running again. So very easy to include these kind of geometrical details and see their influence on the flow field, because we could see the flow field was well captured. Okay, so I think we're on time for questions and answers.
Okay. Thank you very much, Rudy, for presenting us these results, and thank you all for sending us your questions. I have already answered in private most of your questions, but we will take also 5 minutes now to answer a couple of them. For the rest of the questions, we will try to answer them one by one later by email. So the first question for you, Rudy. So did you, we will receive this question from many attendees. What is the computation time of the simulations?
Okay, that's a good question. Indeed, yeah, I didn't include that, but approximately for, like, for example, the polar curve, each of the angle of attack was one simulation. And for those simulation, approximately, I think the computational cost was around 6 or 8 at most thousand CPU hours. That means on 100 cores, it would be around 60 hours of calculation. So it's pretty fair because it's an unsteady simulation with LES, so high fidelity turbulence modeling, and that's extremely competitive, I think, compared if you wanted to run the simulation with that level of quality on a Navier-Stokes code.
Okay, thank you. And second question is, I think it's from an aeronautic engineer. So he's asking for if you can explain what is the configuration of the flap and slat in this workshop. The configuration of the flap and slat.
Yeah, that's an excellent question, and to be honest, I don't remember it at all. So what I suggest is to go on the High-Diff Prediction Workshop website, because all the details on the configuration indeed are there. You can also download the geometry and check on the configuration yourself. So I don't really remember, to be honest, the configuration, which was different, by the way, between the case 1 and case 2, slightly different. But I don't remember, sorry for that.
Okay, no problem. We'll send you. Yeah, we'll try to send the answer maybe later by email. So this way, everyone will get his answer. So maybe we'll take a last question. So okay, I will just pick one. So did you compare the results of the pressure coefficient distributions for the cases 2A and 2C also?
Yeah, that's a good question. We wanted to do that because there is data for pressure distribution on the case 2A and 2C. Unfortunately, we didn't have time to process those data, extract those cutting planes and then distributions, and then compare them with experimental data. The reason is, well, we were limited in time, of course, but especially after we obtained a pretty good polar curve, polar estimation. Let's say we wanted to have an insight in the flow through the oil path images, which is a nice insight, I think, in the flow. And well, we had to make a choice, and we couldn't manage to find time to post-process the pressure data. But it would be interesting for the future, though.
Okay, this will be the last question. Sorry for for that, Rudy.
No problem.
Okay, so this is the last question. Is the mesh refinement automated, and how long does it take to refine to refine? If
Okay, so in this case, the refinement, that means, for example, if I want to go from a coarse to a medium mesh, I just have to change number and generate the new lattice structure again. That takes basically like what we mentioned on the slide of the grids, which is about maximum when you have 100 million elements, about a half an hour on 6 cores. So it's a pretty quick process. We didn't have any sort of adaptive refinement in this case because we were running with a fixed lattice topology, not dynamic and changing lattice structure against time. So it was fixed in time. So we just generate the lattice first and keep it constant along all the simulation. And we basically just refine near the walls, so there was no much time spent on trying to fine-tune the regions of refinement, which are, in this case, mostly refining near the wing profiles because that's the most important critical regions.
Okay, so thank you very much, Rudy, for answering the questions and for the entire presentation. I think we will stop here for this webinar. Please, if you have more questions, you can send them to me by email. You have my email right here in the slide. Feel free to send us any questions. So thank you to everyone who has attended this webinar. I inform you that this webinar has been recorded. You will receive an email notification tomorrow as soon as the recording is uploaded. This way you can review the webinar or share it anytime you want. Thank you again to everyone and have a nice day. Bye-bye.
Thank you, everyone. Bye-bye.